We tend to think of the air all around us as just one big thing. But the truth is, Earth's atmosphere is a lot more like a layer cake. It's got these distinct, absolutely crucial layers stacked one on top of the other. So today, we're going to take a trip up through that cake from right here on the ground all the way to the edge of space to really understand our planet's invisible shield. Okay, so let's just dive right in. If you climb a mountain, it gets colder, right? Simple enough. So you just expect that trend to continue all the way up. But it doesn't. Not even close. The temperature of our atmosphere does this bizarre zigzag. It gets cold, then it gets hot, then it gets cold again, and then unbelievably hot. The central puzzle we're going to solve today is why? All right, so our journey starts right here at home, in the layer where we live and breathe, and where all of our weather happens. This is the troposphere. And the name really says it all. The troposphere is all about constant mixing and churning. Warm air rises, cool air sinks. This whole process is called convection, and it's the engine that drives every cloud, every storm, every single breeze you've ever felt. It's a really turbulent, dynamic place to be. So why does it get colder as you go up in this layer? Well, it's just basic physics, really. As a little parcel of air rises, there's less pressure pushing down on it from the air above. This lets it expand. And you know how letting the air out of a tire feels cooled? It's the same idea. That expansion uses up energy, which makes the air lose heat and cool down. Now, this cooling happens at a pretty set rate, but it's not always the same. Dry air, for example, cools down pretty fast. But our atmosphere isn't dry, is it? It's full of water vapor. And as that moist air rises and cools, the water condenses out to form clouds. And get this, that process actually releases heat, which fights against the cooling effect. It's kind of like the atmosphere has its own little built-in heating system. This cooling trend keeps going all the way to the top of the troposphere, which is about 10 to 16 kilometers up. At this ceiling, which we call the tropopause, it is absolutely frigid. We're talking a minimum of around minus 56 degrees Celsius. That is seriously cold. But this super cold layer isn't just where the weather stops. A better way to think of it is as a gatekeeper. It forms this powerful barrier between the churning, turbulent air below and the totally different layer above. And its job is, well, absolutely vital for life on Earth. So here's how it works. This cold trap is so intense, it forces pretty much all of our planet's water vapor to condense and freeze, so it falls back down to Earth. Without it, water molecules would just drift higher and higher, where intense UV radiation would literally blast them apart. Then the super lightweight hydrogen atoms would just escape into space. Forever. This one single layer is what keeps our planet wet and alive. Now, as we punch through that tropopause, we enter a totally new world, the stratosphere. And in here, the rules of temperature get flipped completely upside down. That's right. After getting colder and colder and colder, the temperature suddenly starts to climb again. This is what's known as a temperature inversion. The air is obviously not getting its heat from the ground anymore. So what's the furnace in the sky that's heating this layer from the top down? Well, the answer is one single incredible molecule, ozone. The stratosphere has this thin layer of ozone that acts like the planet's sunscreen. It intercepts all this harmful high-energy ultraviolet radiation from the sun, and by absorbing all that energy, it heats up the air around it. And what's really amazing is just how little ozone it takes to get the job done. I mean, even at its peak concentration, ozone only makes up about 10 parts per million of the air. It's a tiny, tiny trace amount, but it is powerful enough to absorb so much energy that it completely reverses the temperature trend for an entire layer of the atmosphere. In fact, this ozone-powered heating is so effective that by the time we get to the top of the stratosphere, around 50 kilometers up, the temperature has climbed all the way back to a pretty mild minus 2 degrees. That's a 50-degree jump from the frigid tropopause right below it. And this warming has a huge consequence. When you have warmer air sitting on top of colder air, you don't get any of that churning convection. The stratosphere is incredibly stable and calm. This is actually why commercial jets love to fly in the lower parts of this layer. They can get above all the bumpy weather in the troposphere and just enjoy a nice, smooth ride. All right, buckle up. We're about to leave these relatively gentle layers behind and just blast through the extreme upper limits of our atmosphere, where the temperatures go completely wild. Just look at these numbers. As we head into the next layer up, the mesosphere, the temperature just plummets again, even colder than before, down to minus 92 degrees.
But then, in the layer right above that, the thermosphere, it skyrockets to a mind-boggling 1200 degrees Celsius. So, what on earth is going on?
Well, the mesosphere gets so cold for a really simple reason. There's nothing there to heat it up. We're way above the ozone layer now, so there are no gases to absorb the sun's radiation. It's here, in this intensely cold region, that most meteors vaporize when they slam into our atmosphere, creating those beautiful streaks of light we call shooting stars. And what about the incredible heat of the thermosphere? While this high up, the air is extremely thin, but the few molecules that are floating around get absolutely bombarded by the sun's most powerful radiation. We're talking X-rays and extreme UV. This superheats them to incredible temperatures. It's also where you see the auroras, as all that solar energy excites the molecules into putting on a light show. But here's the crazy part. If you were actually there, you'd freeze. Why? Because while the molecules are moving super fast, that's temperature, there are so few of them, so far apart they wouldn't be able to transfer any of that heat to you. And finally, we reach the exosphere. This is it, the final frontier, the point of no return. Up here, the atmosphere is so incredibly thin that it doesn't even behave like a gas anymore. Individual atoms and molecules are just so far apart that if they get enough of a kick, they can escape Earth's gravity entirely and just drift off into the vacuum of space. So, we've made the whole journey, from the ground all the way to the edge of space. We've gone from warm to cold, to hot to even colder, and then to the hottest of all. Now let's put it all together and see why this complex atmospheric layer cake matters so much. So here's our whole trip in one simple view. We started down in the troposphere, where that decreasing temperature drives all of our weather. Then we hit the stratosphere, where the temperature goes up thanks to that ozone layer, giving us a protective shield. Above that, the mesosphere gets cold again, burning up meteors for us. And finally, the thermosphere, where temperatures go to absolute extremes as it soaks up that high-energy radiation. You can see each layer has its own unique profile and its own vital job to do. And the ultimate takeaway here is that this whole layered structure isn't some cosmic accident. It's an incredibly finely tuned system that makes our planet livable. The tropopause keeps our water in. The stratosphere blocks deadly radiation. It's not just one shield. It's a complex, multi-layered defense system that creates the stable climate we all depend on. And what all this really shows us is that the invisible ocean of air above our heads is an unbelievably elegant and delicate structure. It's truly the architecture of a living planet, engineered by physics and chemistry over billions and billions of years. And that leaves us with one final thought. We've seen just how critical that tropopause is, acting like a lid, keeping our planet's water from just boiling off into space. So think about this. What would happen to the oceans, to our weather, to life itself, if that invisible lid were ever to fail?